Welcome back. This is week 4. We're going to talk about chapter 6, which is multiple linear regression. And yes, this is the same multiple linear regression that you learned about in Stat 601, but we're going to do it a little bit differently here. We're going to add a notion of predictive modeling to it, and that's going to change things a little bit. And this is really the exciting part of the course, where we start talking about the different models and how do we make predictions. And so we're going to talk about the difference between explanatory and predictive modeling. We'll look at an example with Toyota Corolla prices. Then we'll talk about how to fit the predictive model and assess the accuracy of the predictions. And then in the next video, we will talk about selecting a subset of the predictors. With explanatory modeling, we have a model that looks like this: y equals beta 0 plus beta 1 x1, and so forth. And all of these x's are known as predictor variables, x1, x2, all the way up to xp. The error term is normally distributed, independent, and the goal with explanatory modeling then is to understand or explain the relationship between these x's and the target variable y. And this is what you did when you took your introductory stat course, at least at the graduate level, and you learn about multiple regression. And the idea here was that you want to fit the data as best you can and understand the contribution that the x's make to explaining what's going on in the y variable without overfitting. In other words, this error right here represents the randomness, or the random part, and there's always randomness, and you can never explain randomness. You can understand it, but you can't predict it, you can't forecast it. So with explanatory modeling, we want to explain as much as we can up to that random part, and we can measure the goodness of fit, how much we're actually explaining, with things like r squared, looking at the residuals and p-values and so forth. In predictive modeling, we are looking at exactly the same relationship. Y is equal to this linear combination of x's plus an error term, but we don't really care as much about what the relationship is, or rather what the values of these parameters, beta 2 and so forth, are and how those affect the y value. What we're really interested in is making predictions. And so we do basically the same thing in predictive modeling that we did in explanatory modeling on the training data. We take the model that best fits that, and then we apply that to the validation data, and that is what really tells us how good our model is, and that helps us to understand things like how much overfitting we're doing and that sort of thing. So let's look at an example of predictive modeling using the price of Toyota Corollas. And the idea here is that we want to be able to predict the price of the Toyota Corollas based on their specifications. And so for the data, we've got 1,000 used Toyota Corollas, and included in that are a bunch of variables. The name of the data set is Toyota Corolla 1000.jump. And this is what it looks like. You can see we've got price, age, mileage, fuel type, horsepower, so forth. And here is a description of all of the variables. You can see all of this in the textbook as well. Notice the price is in euros, and you saw that many of the fuel types, at least the first few, are diesel, and there's not too many Toyota Corollas in the United States that are diesel powered, so another indication that this is data coming from Europe. Weight is also in kilograms. So let's start off by doing some pre-processing. Pre-processing is something that you always have to do when you're data mining. In this case, we need to form a partition, or rather look to verify that there is a partition. You'll see that there's already a validation column in this data set. And if you come over here to jump and open up the Toyota Corolla 1000 data set, you'll see we have something that looks like this. And if you scroll all the way over, you'll see there already is a validation data set. So there's a 60-40 partition between training and validation. If you don't like that one, if you want to do your own, you certainly could do that. Add another column in here and make another validation set. Once you run the regression and jump, this is the output that you get. And you can see for each of the variables, we have an estimate for the parameter, for the coefficient, and a standard error for that, and then a t-ratio. then a p-value associated with that. So we want to look for p-values that are less than 5%. Those that are less than 5% mean that we have a significant contribution being made by that particular variable given everything else in the model, or above and beyond everything else that's given in the model. So how do we get this output? Let's go back to our data set, and we're going to go up to Analyze, Fit Model. The price is the Y variable. We're going to throw everything else in here except for the validation. We're just going to drag it down here and drop it. And then for validation, we're going to say use this variable. Now if we had a different validation variable, if we put another one in here, so we wanted to do something different, we could just select that one at this point. So we're going to run the model, and we'll see a bunch of output here. But what we're looking at the moment is the effects, or the parameter estimate. So here we have same exact numbers, what you see in the slideshow and in the textbook, and negative 1412.93, and so forth. And these are all from the training data. So this is fit on the training data from the partition that we made. And if we were to go and score additional data, we would do that by just taking new values for our x's, plug them in here. That would give us a prediction. If we want to see how the model does in the training data and also in the validation data set, we can look for this cross-validation table, and we see the source, training, validation, the R-squared, the root average square error, and the frequency. So this just tells us we've got a 60-40 split, and we see that the average squared error, square root of that, is pretty similar for both of these things. So training set, we do a little bit better than on the validation set. That's something that typically happens in the R-squared. The training set is again in the same ballpark as the validation set. So that's kind of what we're looking for. Where you tend to have problems is when the training set gets very, very small error and high R-squared, and then on the validation set you have very high root average square error and a low R-squared. That means that you're overfitting in the training set, and that is probably a bad model. So we would calculate this for each of the models that we run, and then save the prediction formula to the data table, and then we can use that to do model comparison. In other words, we could look at the validation set on a different model and compare that to the validation outcome, cross-validation data for all the other models that we use. And the one with the smallest RASE is going to be the model that is the one we want to go with. We can also save the residuals and look at those with the distribution table, and I'll show you how to do that in just a minute. But basically what we're doing is adding columns to the data set. So for the training or the validation, doesn't matter, we're going to calculate the predicted formula and the price, and then the residual value, and these are what we are going to then use to analyze with the distribution. So we look at the distribution of the residuals. We see the layout. This should be a bell-shaped distribution if all the assumptions are met for regression, and if it's clear departure from that, then that means maybe we need to rethink the model that we're using. There might be some outliers. We can identify those. We can look at the average error, and you can see that the average error is here, and this is on the validation data, I believe, and we can interpret that. So if the average error is bigger than 0, much bigger than 0, that tends to lead us to conclude that there's some sort of bias in our model, and that may or may not be the case of having an overfit model or some other sort of problem with our training data. So to get the predictive formula, go to the output, and on this little red triangle, click on it, and you'll see save columns and then prediction formula. Click on that, and then if you go back to the data, you should see the predicted formula price. And if you want to get the residuals, go back here to the output, go to the same place, so click on save columns and then residuals. And you can see there's a lot of other things that you can save in there. Now we go look at the data, we see the predicted formula price and the residual for the price. And you can see that those match up with what we have in the slideshow. So how do we get the distribution of the residuals then? Well, we simply go back to the data set, go to Analyze, Distribution, Residual Price is what we want to get this for, so drag that over here. Click OK, and you'll see that we get the same histogram, although it's oriented opposite of how it looks in the slideshow. And to change it, you go to little red triangle, Display Options, and then Horizontal Layout. Now, upon closer examination, this is not exactly what we have in the slides. And why is that? Well, it turns out the residual that I have here is for all of the data. You can see there's 1,000 data points, whereas here we only had 400 data points in the validation set. So in order to get this output, we will come back to the data set, go to distribution, basically do the same thing, residual price, throw that in here, but now we're going to do this by validation. And when we say OK, we now get two sets of output. The first one is for the training data, and you can see that here it says training, and there are 600 observations, but what we're interested in is down here, the residual price in the validation set. And now if we look at this, we get exactly the same thing. We can check out the distribution, and the distribution seems to be skewed a little bit to the right. If we were doing explanatory modeling, we could take the logarithm, and that would change this to look more like a normal distribution. However, when we're doing predictive modeling, that's not necessarily going to be helpful. So we're going to end this video here, and we will pick up where this one leaves off in the next video.